Section 5.6, complex numbers. We're going to identify and graph complex numbers, add, subtract, multiply, and divide complex numbers. Now you're asking yourself, what is a complex number? So remember before, if we were to solve this equation right here, we have x squared plus 1, and that should say equals 0. So if I want to solve this, there is no linear term, so I would do x squared is equal to -1, and then I would get that x is equal to plus or minus the square root of -1. And remember that we said that we can't take the square root of a negative number. Well, that was until today. So we can take the square root of a negative number, and we call those numbers imaginary numbers. And so there is a way to simplify those numbers, which is what we're going to talk about. So for this, let's go ahead and go down to this problem right here. So right up here we have I equals the square root, and that should say negative there, it just got cut off for some reason. So I know that I is going to be equal to the square root of -1. So that's the definition of an imaginary number. So for this, if I wanted to do I squared, then I squared would be the square root of -1 squared. And what happens when you square a radical, it gets rid of it. So I squared is equal to -1. So we can use this in order to help us simplify radical equations. So if we look at this example that we have right here, if I have the square root of -4, well, that's the same thing as if going backwards from what we did before, root -1 times the square root of 4. And the square root of -1 we just defined to be I, so this would be I root 4, and then the square root of 4 is 2, so then we would end up with 2I as our solution, which is nice. So now we can simplify these problems that we have. So let's go ahead and why don't you guys simplify these four and hit pause and then come back to it and we'll do it together. So the first thing you want to do when you're simplifying these is always take out your I first. So this would be I times the square root of 2. The square root of 2 does not simplify any further, so that's the solution. For the next one, I can rewrite this as I root 12. 12 does reduce because remember it's the same thing as 4 times 3 and the square root of 4 is 2. So this becomes 2I root 3. For the next one, we get I times the square root of 81, which is square root of 81 is 9, so this becomes 9I. And then over here, we have a negative in front of the radical, so this would be -I root 343. And then, of course, you want to break that down. That's 7 times 49. Square root of 49 is 7, so this is really equal to -7I root 7. So that's how we can simplify the radicals that have negatives, taking out the I first and then simplifying the radicals. Now, we also want to be able to simplify the powers of I. So that's what we're going to talk about next, simplifying powers of I. So I'm going to do this on a new sheet. So we already said that I is equal to the square root of -1. And we're not going to use that when we're simplifying it. We're just going to leave it as I. So we're going to say I is equal to I. And then I squared, remember we said when we square the square root of -1, we get -1. So what if I did I to the third power? If I have I to the third power, well, isn't that the same thing as I squared times I, because what do you do when you multiply something with the same base? You add the exponents. So we're just going backwards, and we said I squared was really -1, and I we keep as I. So then this is really equal to -I. If I do I to the fourth power, I would get I squared times I squared. This is just one combination that I can do. I could also do I to the third times I if you wanted to. And I squared times I squared is -1 times -1, because I squared is really -1, which we said earlier, and that's equal to 1. If I do I to the fifth power, that's I to the fourth power times I, and I to the fourth power we just said was 1 times I is I. And if we did I to the sixth power, I to the sixth power is I to the fifth power times I, and that would be I to the 5th power is I times I, which is I squared, which we said is -1. So again, I'm just simplifying these powers of I. And I could keep on going, of course. I to the 7th power would be I to the 6th times I. And I to the 6th we just said was -1 times I, which gives us -I. And if I keep going, I could do I to the 8th power is I to the 7th times I, which would be -I times I, which is -I squared, which would be -1 times -1. And notice that if you look at these values from when we started, so I was my first value, -1, -I, 1, then we get I, -1, -I, 1. And if I were then to do I to the 9th power, what do you think you would get? I to the 9th power should give me, in this case, we're starting our cycle over, so it should give me I. So if I do I to the 8th times I get 1 times I, which is I. So notice that because of that, we're starting to see the same pattern over and over. And then we're starting, so I to the 10th power is going to be equal to -1, I to the 11th power, so we could keep on going. So this would be the 10th power, 11th power, 12th power, and then 13th power. And because of that, they're going in cycles of 4, we can use remainders in order to help us determine what the powers are going to simplify into. So this is what I was just talking about. So if I wanted to simplify I to the 23rd, well, I'm not going to just count 1, 2, 3, 4, 5, 6, 7, 8, and keep on going. I'm going to divide 23 by 4 and see how many times it goes in and what the remainder is. So 4 goes into 23 5 times with a remainder of 3. That means you're on the 3rd cycle of I, which would be -I. So in this case, I to the 23rd is equal to -I. And we can do this with any powers. What's easier to look at is looking at your remainders. So if I have I to the 1st power, when you have a remainder of 0, you're going to be on the 4th cycle, so that would be equal to 1. If you have a remainder of 0.25, that's like saying you have 1 out of 4, so then you would be equal to I. If you have a remainder of 0.50, that's like 2 out of 4, so that would be I squared, which is -1. And if you have 0.75, that would be 3 out of 4, so if you have 3 out of 4, this is going to be equal to -I. So that's what you can do on your calculators, look at these remainders to tell you what you have. So let's do some practice examples. So looking at the first one, I have I to the 40th power. So it means I want to divide 40 by 4 and see what my remainder is. So when I do 40 divided by 4, I get, in this case, it's equal to 10. So because of that, there is no remainder, so the remainder equals 0. Because of that, I know that this is on the 4th cycle, so I to the 40 simplifies into 1. So if I do I to the 41st power, when I divide 41 divided by 4, I get 10.25. So that 0.25 tells me I have 1 out of 4, so that would be I to the 1st power. So I would be my answer. I know 42 divided by 4 gives me 10.50 when I divide it. Because of this 0.50, I have 2 out of 4, so I'm on the I squared cycle, which means I squared is -1. So -1 would be my solution. And then 43 out of 4 gives me 10.75. So that's 3 out of 4. So this is the same thing as I to the third, and we know I to the third is really negative I. And that's how you're going to simplify these. So why don't you guys do E, F, and G and pause it, and then unpause it. So then for the first one, 8 divided by 4 is no remainder, so then I know this is going to be equal to 1 when you simplify it. I to the 77, so 77 divided by 4 is 19.25, so that would be I to the first, so just I. And 102 divided by 4 gives us 25.50, so that means you have I squared, which is really just negative 1. So I to the 102 power really simplifies into negative 1. So those are the powers of I. So anytime you have anything that's not, when you're simplifying it, I to the first power, then you want to simplify it using our power rule. Now, you're wondering, where do these imaginary numbers fit into what we already know about the real number system? So real numbers, remember, break into rational numbers and irrational numbers. Then we have rational numbers, integers, whole numbers, natural numbers. So remember, natural numbers, you are your counting numbers, 1, 2, 3, 4, etc. Whole numbers is when we introduce 0, 1, 2, 3, 4, etc. Integers is when you have negative numbers, whole numbers, and natural numbers, and of course no decimals. Rational numbers, when you have decimals that are terminating or repeating, can be written as fractions, and real numbers is made up of everything. So now imaginary numbers, we are on the other side from real numbers, and for these imaginary numbers, we have numbers such as 4i would be imaginary because it has an imaginary part, 2i root 2, the square root of negative 5, because remember that's really I root 5, 3, we'll do that part next. So these are all imaginary numbers. So a complex number has two different parts. So complex numbers are always in the form of a plus or minus, depending on what it is, b, I. So it has the a, which is the real part, and the b, which is the imaginary part. So a is the real part, and bi is the imaginary part. And every number can be written as a complex number. So for example, if I had 4i, this is a complex number because I could write 0 plus 4i. If I had just like the number 3, we can write this as a complex number because it's really 3 plus no imaginary part. So I can also have both a real and imaginary part. So like if I had 1 plus 7i, this would be a complex number because I have the real part, which is 1, and the imaginary part, which is 7i. So for the next example, it says, write each complex number in a plus bi form. So that means complex number form. So the real part goes first, the imaginary part goes second. So first we have to simplify this. This becomes I root 9 plus 6. The square root of 9 is 3, so this is 3i plus 6. This is not in complex number form because the 6 needs to go first. So this would be 6 plus 3i, and this would be my solution. So let's do the next one. For the next one, I again do I root 121 because you always want to write your equations in terms of I before you simplify them. The square root of 121 is 11, so negative 7 and then plus 11i would be my solution. If we go to the next one, I root 18 plus 13. The square root of 18, we need to simplify, so that's 9 times 2. So when we do this, we get 13 plus, this would be 3i times the square root of 2. And that would be my real part's 13. My imaginary part is the 3i root 2. And let's say I had another problem, d, negative 12. So if this was my solution, this is not in complex number form. I have to write it that way. It doesn't have an imaginary part, so I would write this as negative 12 plus 0i. And again, you can do that with any number. So the next thing we want to talk about is operation with complex numbers. So we have what's called the additive inverse. The additive inverse, if the sum of two complex numbers is 0. So when you add something up and you get 0, it's an additive inverse. So for example, -3 is the additive inverse of 3 because -3 plus 3 equals 0. And 4 is the additive inverse of -4 because 4 plus -4 equals 0. So it says find the additive inverse of each complex number. So when we add these together, we want to get 0. So 2 plus a positive 2 would give me 0, and minus a 5i. So 2 negative and positive 2 is 0, and this would give me 0. So that means that my additive inverse would be 2 minus 5i. We change both signs. This is different than the conjugate. We're not changing the sign of the second term, we are changing both signs. So this right here is not written as a complex number for b, so the complex number form would be 0 minus 10i. So then for this, my number would be 0 plus 10i. So that would be the additive inverse, positive 10i. So for this last one, you would get negative x plus yi. So for the next part, when you're adding or subtracting complex number, you are going to combine the real and imaginary parts separately. So for this, just like when you're combining like terms with variables, you think of it as the same way. Now for number or letter A, I don't have to distribute anything here because there's just a plus and there's a 1 in front of the parentheses. So I can drop those parentheses and I can combine my like terms. So 5 minus 2 gives me 3, and then I have the 7i and the 6i, which are like terms, and that gives me plus 13i. So 3 plus 13i would be my simplified version. So if you look at B, notice we have this negative here, which needs to get distribute to each of these. So 8 plus 3i minus 2 minus 4i. Now I need to combine my like terms. So 8 minus 2 is 6, and 3i minus 4i gives me minus I. And notice I'm always writing it in complex number form, the real part and the imaginary part second. So over here, same thing, 7 minus 3 minus 2i, don't forget to distribute that negative, and combine your like terms, so this would be 4 minus 2i. And for the very last one, same thing, I don't have to worry about distributing anything, so this ends up being 4, and then negative 6i plus 3i gives me minus 3i. The next part that we're going to talk about is multiplying and dividing complex numbers. When we are multiplying these complex numbers, to multiply them out, you're going to multiply them like you would multiply any numbers. So -4 times -3 would be -12, and I times I, you're multiplying something with the same base, so you add the exponents, gives me I squared. But I squared simplifies, so we have to simplify this. -12 times I squared, remember we said was -1, so then this would be equal to 12. So then if you look at B, we have I to the 5th times 7i squared, so this would be 7. I to the 5th times I squared, add the exponents, so I to the 7th. I to the 7th can reduce because it's larger than I. So then I to the 7th power, remember we take that 7 divided by 4 and look at our remainder to help us, so we get 1.75. So that really means 0.75, we're on the third cycle of I, so this would be I to the 3rd, which is, remember, negative I. So for this would be negative 7I. Because we reduce that I to the 7th, because I to the 7th is really negative I. If we do the next one, we have to distribute. So we get 15i plus 5 times 4 is 20. I times I is I squared. And then, of course, remember I squared reduces. And so then that would give me negative 20 plus 15i if we write it in complex number form. So then for the next one, again, for this one we have a binomial times a binomial, which means you need to box this or FOIL it. So if I FOIL this out, I would get 10 minus 2i plus 5i, and then minus I squared. and we have like terms, so 10 plus 3i. I squared is really -1, so minus -1. So that becomes plus 1, so we get 11 plus 3i. So I would pause it and see if you can do the next two on your own. And then I'm going to do them with you. So for E, 8 times 8 is going to give me 64. And then we have plus 56i, and then minus 56i, and then minus 49i squared. Notice that these terms cancel out because it's plus and a minus. So we have 64 minus 49 times -1. Where's that -1 come from? Because I squared, remember, is really equal to -1. So we have 64 plus 49, which is 113. And if you look at these terms, notice that the terms are the same except for the sign of the second term is changed. So we do have conjugates for complex numbers, so these would be conjugates. And remember, we said when we multiply conjugates together, it gets rid of your radicals. So remember, I is really a radical, so root -1, so that makes sense that it would be gone and just the real number would be left. So for this next one, notice you would have to, you have 2i squared, so 2 minus I squared, sorry. So if you write it out, you'd have to FOIL them all out. So you should do this on your own, and when you do this, you should end up with 23 minus 14i. So do that and then check your answer. So why are we learning about imaginary numbers now? The reason is because we can use imaginary numbers to solve quadratic equations that don't have real solutions. So what does that mean? So when the parabola doesn't cross the x-axis, remember there are not any real number solutions, aka no zeros or roots. However, there are two imaginary solutions to each of these equations. So if we look at this first equation right here, I can solve this using square roots because I don't have a linear term, so I can subtract the 48 to the other side. So when I do that, I get 3x squared equals -48. Divide by -3, I get x squared is equal, by 3, not -3. X squared is equal to -16. Get rid of the power, so x is equal to plus or minus the square root of -16, and that negative, remember, you take it out, becomes plus or minus I root 16, and the square root of 16 is 4, so x is equal to plus or minus 4i. These are my two imaginary solutions for my equation. Now if we look at b, then we can do the same thing. So divide by -5. Take the square root of both sides. Don't forget your plus or minus. Take out the I. And then the square root of 30 doesn't reduce, so plus or minus I root 30 is my solution. And the last one, so 2 divided by 8 reduces into 1/4. Remember, we don't like fractions underneath radicals, so I'm going to take out the I and then separate them. So this is plus or minus I root 1 over the square root of 4. The square root of 1 is just 1, and the square root of 4 is 2. So this is really plus or minus I 1/2 I, or you could do I over 2. That's the same thing. So we're going to stop here, and we will finish the rest of this in class, but make sure you bring this with you.